Welcome to another tutorial about the Supply Chain Management League competition. This time I want to speak about the ways in which you can structure your agent. There are, in general, two main strategies. The one on the left is what we call all-in-one agent. So this agent responds directly to the callbacks that we described in the previous tutorial. So it for example, decides what to do in a respond to negotiation request call, or what to do in sign all contracts call. It has to decide each one of these. The functionality in this case is distributed between callbacks, okay? And everything is in one place. So everything that happens during a sign all contracts call is in the same piece of code. You can read all of that at once. That is sometimes useful in understanding what's happening, but it's harder to reuse because the agent is naturally decomposed into components, as we will explain later. And if you want to reuse components from different agents, it's better to develop it in a component-based way, as we will describe in the other approach. As an example of this development strategy, in the skeleton that you download to start developing your agent, you will find a file called myagent.py. This one uses this all-in-one agent design, so it has callbacks, all the callbacks in them, and you just override what you want. The other possibility is component-based agent, what we call a component-based agent. This agent is decomposed into several components that are reusable and services. The difference between a component and a service is that a service is something that the agent creates and uses. Examples of services in the system are controllers. You can think of negotiators as services, as well as a simulator. So the system has a simulator which is distinct from the actual system simulator that runs the simulation. That's a simulation of the simulation. It allows you to predict what will happen in your factory in the future. But these are examples of services. The components are a little bit more complex. Components can be combined together to construct an agent. So in this case, functionality is distributed not between callbacks, but between components. And these components are reusable. So that's why all of the built-in agents are developed using components. That allows us to mix and match these components to create new strategies. As an example of how to use that, you can look at the myagent2.py file, which you will find in the skeleton. I'll put a link to that in the description. Okay, what are these components? What is a component? So a component is simply a Python class, but it has very specific structure. And its documentation always reflects this structure. First, it has a set of attributes that are used to construct it. So these are parameters that allow you to control how this component works, and they must have default values in our implementation. The second thing is a set of requirements. In the documentation of the component, you will find that under the section called requires, it lists a set of data members or methods that the agent expect to exist in the component expect to exist in the agent. I'll give an example of that later during this video. But if this data member or method doesn't exist in the agent, the component will simply fail to act. Okay. The third component is a set of hooks. So any component can actually respond to any callback. There are two ways to do that. One of them is what we call hooking. In this case, the callback, the component responds to the callback. Let's say, for example, the step callback. So it decides what to do during the step callback. But it then, or before doing what it does, calls super, which allows other, sorry, that's not other agents, that's other components. That's other components on the agent to use the same callback. So you can have as many components using the same callback as needed. That means that when you are developing the component, you don't really need to think about what are the other components that will exist in the agent. It just should hook into the callbacks it needs to do its job. The other thing is that agents can override callbacks. By overriding a callback, it just does something, then it does not call super. In the description of every component in the system, we distinguish between these possibilities clearly. So when a component hooks into a callback, this callback is listed in the hooks into section, and when it's overriding it, it's listed in the overrides section. Okay, that's how components can have access to what's happening in the world and deciding what to do. Based on that, they provide either data members or methods that other components and the main agent can use. That's always described in the provides section. Finally, each component type can define a set of abstract methods that any class that inherits from this component, so any specific implementation of this type of component must implement. So these are all the components of a component. And notice that not every component have all of these. Some components, for example, do not have any abstract methods. Some components do not require anything. Actually, most components do not require anything. Okay, that seems very abstract. Let's just go into specific details. Before we go to that, as a rule of thumb, you should hook into step, init, and any callback that starts with on, because these are giving information to the agent, so you should allow other components to receive that information if they need it. But you should override everything else. For example, sign contracts. There should be that the same agent should not have two components that are responsible for signing. One component should implement all of the signing logic. Okay? Now, what are the components that we actually used in our system? Please notice that that's our design decision. You do not need to do the same. You can divide your development in any way you like. You do not even need to use component-based development. You can use an all-in-one agent design as we described before. But we decided to use the following components. So these are the main components we are using. The first one is the trading strategy. The trading strategy is just giving a very high goal to the agent. It tells the agent what it should aim at. Then the negotiation manager is responsible of actually achieving that through negotiations. And it uses a signing strategy to decide what to sign. Then there is a production strategy which tells the factory what to produce. Okay, so these are the four main components. Now, in terms of what we described before, what does each one of these provide and what are the types that are actually implemented? So in general, the trading strategy provides 4 state variables. Needed inputs are the inputs that are needed at every time step. So the agent should buy these. Needed outputs are the outputs that are expected, not expected, that need to be achieved by the negotiation manager. So these are the targets of the sales force of this factory. They should sell this amount. The secured inputs and secured outputs will just keep how much of the needs are already satisfied for each step. So the trading strategy provides all of these 4 state variables. To achieve that, the trading strategy, some trading strategies, as we will describe later, use subcomponents. One of them is the trade prediction strategy, which just predicts what will happen in the future. So it predicts how many inputs should I expect at every time step in the future, how many outputs should I expect, what is the cost at which I should expect inputs to be available, and what is the price I should expect to sell my outputs at. Of course, this can easily be used to generate the needed inputs and needed outputs by the trading strategy. The other part is the execution rate prediction strategy. This one provides a predict quantity method. So it allows the trading strategy to know for any contract how much of the quantity in this contract is predicted to actually be executed. Okay? That is useful information because it can tell it how should it update its secured inputs and secured outputs. Now the negotiation manager, the second major strategy, it requires, just to use the same term used in the previous slide, it requires 2 things, a target quantity and an acceptable unit price. So you need to tell it what is the target quantity and what is the acceptable unit price. Then it just goes and does the negotiations. It creates negotiators, creates controllers, and have them achieve this target through agreements. These agreements are then passed to the signing strategy as well as the prediction optionally, and then you can use the signing strategy to construct actual contracts, actually sign them into contracts, and these contracts are actually used by all what to do. Okay? This is the general structure of the agent. I know it seems very abstract, very high level, so let's go into more details. Let's check each one of these, and you'll find that the ideas are extremely simple. So, the production strategy. The production strategy decides what should be produced by hooking into the step function. Okay, it can hook into other functions that will be in the description of the specific production strategy you are using, and these are all defined in the production module under the components package. There are 3 main production strategies in the system. The first one is supply-driven production strategy. It makes the agent produce as much as possible. So whenever some inputs are available for it, it generates the outputs. That has the risk of doing too much production and not being able to sell it in the future, so you lose the production cost. That's why there is another strategy, which is called demand-driven production strategy. It simply produces enough to satisfy all signed contracts, assuming full execution. You can see here that you can immediately improve that by using an execution rate prediction so that you don't really assume full execution. You can be more intelligent. But all of the built-in strategies are extremely simple because the goal is to provide a baseline. Finally, there is the trade-driven production strategy, which is the most complex of them. It produces only for contracts that the agent did not initiate. So it acts like the demand-driven production strategy, but it ignores contracts that the agent have actually initiated because it assumes that these contracts are there because the agent needs these. So it should not add more production to achieve them. What about negotiation? So the negotiation manager requires 2 things, a target quantity. If you have a trading strategy, you can just calculate this as the needs minus the secured amount. It's very easy to calculate in this case. If you don't, you have to implement that in your agent somehow. Give it a target quantity for each time step, and give it an acceptable unit price for buying and for selling. There are 3 negotiation managers in the system. The independent negotiation manager, it asks you to also define a utility function, and then it uses this utility function for negotiation among independent negotiators. So these negotiators do not take into account that other negotiators exist in the system. You can see that that can lead easily to more contracts that you need. Then there is the moving range negotiation manager. This one creates one controller for handling all buying and another one for handling all selling. This controller will try to keep these negotiations running in synchrony so that you don't over-contract. And it only considers potential contracts within some future range of steps. It doesn't look to the infinite horizon, just for some horizon in the future. It uses a sync controller, which utilizes a simple linear utility function. So in the implementation we have, the utility function is just a linear combination of how far is the quantity from the target quantity and the price. And then there is a step negotiation manager. This step negotiation manager creates one controller that's responsible for every negotiation step. And it tries to achieve the target of this step, then stop any negotiations on that step after that. These step controllers are responsible for achieving the given target, and they use a step controller, that's a service, which utilizes an internal meta-negotiator to handle the negotiations. That's a mouthful, but what's actually happening is that this step controller that we implement treats all negotiations in the same way. So it uses the same negotiation algorithm in all of them. Of course, that can be improved upon. The goal of the negotiation manager is to start proactive negotiations during step and in response to signing contracts, and it uses the acceptable unit price to set up the agenda. Okay, so that's the second component, the negotiation manager. The third component is the signing strategy, which is used by other components. It decides which contracts to sign. So this component, we have two implementations of it. Sign all simply signs everything. Whatever contract, whatever the negotiators say is good. And sign all possible. This one signs all buy contracts without thinking. But for sale contracts, it just does a very small check. It checks that this contract makes sense. For example, if a negotiator agreed that you will produce 100 items of your product by the next step, and you only have 10 lines, it makes no sense to sign this contract. These are the contracts that will not be signed by this strategy. Sorry. Everything else will be signed. Okay. What about the trading strategy? As we said, the trading strategy controls the overall strategy of the agent. What it wants to buy, what it wants to sell, and keeps track of how much of this is actually achieved. We implemented 3 trading strategies in the system. The first one is a no trading strategy. It simply sets everything to 0. So the agent doesn't want to do anything. It doesn't decide to do anything. This agent is mostly reactive. The second one is reactive trading strategy, not to be confused with a no trading strategy. In this case, this agent will increase the secured inputs when a sell contract is signed, assuming full execution, do the same for outputs, assuming full execution, but keeps the needs always at 0. So says, I don't need anything, but I'm having extra all the time. How can this be useful? Not much. That's why reactive agents that are based on this trading strategy are not very useful. They do not achieve that well in the simulation. The most successful trading strategy is what we call the prediction-based trading strategy. It uses 2 subcomponents: a trade prediction strategy to initialize the needs, and an execution rate prediction strategy to update the secured quantities whenever it knows that a contract was signed. It increases secured inputs when a sale contract is signed based on the ERPS result, and the same for the buy contracts. sorry, it does not keep needs at 0. That's a mistake, sorry. As we said, it uses two subcomponents, the trade prediction strategy and the execution rate prediction strategy. What are these doing? The trade prediction strategy predicts future trade. So it tells you how many inputs to expect at what price at every time step, and how many outputs should you expect at what price at every time step. It's easy to learn that using machine learning offline, and just use whatever you learned online in the simulation. And it's also a chance for you to apply online machine learning to improve these models. But what we did in the actual implementations we have is pretty simple. We have one trade prediction strategy, which is fixed trade prediction strategy. You just give it numbers. So, for example, it will always expect that it will have 5 inputs, 5 outputs at catalog prices for selling and buying. That's it. Of course, it's a very clear point to improve. If you can improve the trade prediction strategy, you will improve the trading strategy of the agent, which will improve the targets given to the negotiators, which in general will improve the actual behavior of your agent by providing a better utility function, effective utility function for it. The last component is the execution rate prediction strategy. This one provides a predict quantity. So you give it a contract and it tells you how much should you expect from the quantity in this contract to be executed. Again, there are many ideas here. You can use the financial reports and the past behavior of agents to predict what will they do in the future. You can also look at what happened previously in similar simulations. Again, machine learning can be used a lot here. But what we did is, again, extremely simple. We have 2 execution rate prediction strategies, ERPS for short. One is fixed, just it predicts 0.5. Everything will be executed by 0.5. Half of all contracts will not be executed. And the second one is mean prediction. So it simply predicts the average execution fractions that happened in this world simulation online. Again, it has some prior, which is 0.5, just everything will be executed by half, and then it updates that based on what's happening. This 0.5 is an example of an attribute. So actually, the way it is implemented is that that's an attribute. You can create mean EPR strategies with different prediction fractions, and you can compare them, find the best one, and use it in the competition. That's very easy to do. Okay, so that's it for today. That's what I wanted to explain. What are the components and how to use them? In the next tutorial, I actually try to do that by developing an agent based on some of these components and adding new components. You can find a tutorial in the documentation that describes all of these details, which is the second tutorial. Thank you for listening.